All right, everybody, good morning. It's 10 o'clock, so we're going to get started. In the case anybody else is joining in a little bit late, that's okay. Welcome to take a look at the recording once we get it posted. Today, we're going to be stepping into some more dense material. So this is going to be one of those times where, like I said last time, if you have your webcam on, I'm going to be looking to you all for like some feedback. You all let me, like, if you're confused, you can like signal to me. If you're kind of feeling it, we can move through it faster. If you don't have your webcam on, this is my last kind of implore that you do consider it, because this is where things get a little bit dense, and the more that I can calibrate to what your feeling of understanding is, the better this lecture is going to go. Now, that being said, there is a lot that's going on here. Don't feel like you need to write it all down. The reason why I have the guided notes is because I'm going to help carry the bulk of this for you. So I'm going to have, like, in the guided notes, we're going to have like the explanations, the big formal long proofs. I've got that for you already. So what I'd recommend you write down is you write down anything I write down, right? Because anything that I write down is going to be things that I'm helping you fill in for the eventual guided notes. And the second thing is I would recommend that you write down things that help you recall just the general gist, the summary. So when we go through the proofs, the way I've structured the proofs for just about everything that's large and dense, we're going to talk about a strategy. We're going to be like, here's how we're about to tackle this thing. Like, this is the story I'm about to walk you all through, the logical exploration. And then we'll do it. And so on the guided notes, often I will give you the proof, but I'll leave a nice little blank space in there for you to write down what's the meaning, like what's the intuition, what's the strategy, what's actually happening in all that crazy paragraph long, page long math stuff. Like, it's a way of you all kind of making sense and decoding it. So we're going to do that together. So again, don't feel like you have to write down everything on the slides. The slides will be made available. The guided notes I'll show you or give you a preview to at the end, so you can see how much there is in the guided notes. And remember that it should be part of your cadence for this course that when you finish the lesson, you should go to print off the guided notes as soon as possible, because like we mentioned in the learning how to learn article for week 0, most of what I teach you will forget in an hour. Like, that's just human nature. That's just how it works. So you want to try to capture as much as you can while it's in your brain and fresh, and then you can use those guided notes as a nice way of refreshing as you study throughout the week. So let's go ahead and get started. Let's just do a little bit of a warm up here. So this is just to see who all wrote down some things from last class. We got a poll that you should see on your end of the screen. Now, this is not to say what is the correct definition, but it is to ask what is my definition of math, the one that I will be promoting this semester. So let's see what we get. All right, I think that should be just about everybody. Okay, so you can go ahead and see the results on your screen. This is a little bit of what I was kind of telling you about. Pretty much all of the last class was dedicated to this one 4-word definition. And we've already got some people who kind of lost a little bit of it. So like, this is a chance to show you all, like, I can talk up here for an hour, but you really want to go and print off those guided notes. If you'd print those guided notes off, it would have walked you through this. You'd have that as reference. So you want to make sure you're doing that after every single class. Otherwise, you will forget too much. Too much will go over your head. It's too dense. So like, really do make sure that you're considering doing that every single day after class. Yes, it's a lot of printing. Yes, I understand that printing can be expensive. I promise I'm not going to ask you print more than 1,000 pages. And even if I asked you to print 1,000 pages at 10 cents a page, I'm saving you money because we don't have to buy the book for this class, and I'm not asking you to buy the Cengage code. Together, that would be like $250. I'm not going to charge, like, it's not going to be anywhere near that expensive to print off the guided notes. So just do it. Really just do it. All right, so let's go ahead and jump in. The correct answer is C. Now, that's not to say like that's the correct definition, but that's the definition I will be promoting. Math is a model of logic, meaning that if you at any point are just doing math on your paper, you're moving the symbols and you're following the steps, but you don't understand why it works or what you're doing, just understand like you're wasting your own time, because that's worthless. Like, it's a computer could do that for you. You aren't contributing anything. Your goal in this class is to make sense of why all of those things work, to try to understand and decode the symbols and the story behind them. And I'm going to help do that with you. So today we're going to start from the ground up. We're going to build up from some very, very basic things, because in my classes, rules are not, like, they don't belong in my math class. There's no such thing as a rule in math. We've got this, it's a model of logic. It's got to make sense. Otherwise, there's no point in us doing it, right? These are not techniques that we found on stowed tablets. These are not techniques that were bestowed upon a higher power. Like, these are things that were man-made, so we can absolutely, like, decode that. We can be able to get back into the mindset of the logic that people were trying to model. So we're going to start from the bare bones. We're going to talk about numbers. What are they? Where'd they come from? Why are some called imaginary? Why are some negative? How can we represent this? Because after last class, you probably left feeling a little bit like philosophically challenged. There was a whole bunch of does 1 equal 0 or does 0 equal 10 kind of things, and it can be sometimes a little easy to step away from that and go, well, maybe numbers are just numbers. Maybe I've just been lied to all these. Like, we're gonna try to give a solid foundation that helps us understand, why are these numbers different? Why did they evolve? And how did we get the numbers that we all take for granted today? So let's talk a little bit. We've got science. We said that science changes and math does not change, right? In other words, we're not going to figure out that 1 + 1 = 2 only sometimes. And we got to figure out why that is. What about infinity? I've heard infinity is not a number. I've heard that from a bunch of different people. But if you Google infinity, it comes up as a number, like it's in the definition. It's called a transfinite number. So it is a number. So it's absolutely a number. Yet I know a whole bunch of math teachers, my colleagues included, who go, infinity is not a number, it's an idea. Anybody ever hear that? Give me a nod if we ever heard, like, infinity is not a number, it's not. Yeah, that's crazy. All numbers are ideas. That makes no sense to me. It's like, why wouldn't it be a number? So we're going to talk about what that is. Is there a smallest number, a largest number, and are negatives real numbers, but imaginary numbers aren't real? Like, we're going to talk a little bit about where that all came from. So let's do a little bit just to kind of wake up the chat here. I'd like y'all to kind of throw in, try to define numbers for me. So you get the chat open. Just give me what are numbers to you? Let's get some ideas. And again, if you find an idea you like, you can quote it, just cite that person, be like, I like what this person said. That's cool. Oh, value. Okay, so we got value. We got counting of something, a way of counting. A symbol to represent a quantity. Okay. So some things to consider. If we talk about negatives, you can't go out and count negatives, right? You can't count debt. That's something that is purely made up from its origin. So numbers might be a little bit more than just physical quantities. On top of that, what about hours on a clock? That's not a physical quantity. We can't capture that, right, as something we hold in our hands. So it might not be something that has to be physical. On top of that, what about computers? Computers speak in binary. They swap ones and zeros across all the time that just represent true, false, yes, no, on, off. So numbers might just be a state. It just might be a state of, like, it is on, we'll call that 1. It's off, we'll call that 0. Right? So it doesn't have to always be quantities either. Measurements are great. That's a good idea. But again, like, where does that work with it being labeled as a state? So again, it's a broad, big definition, what are numbers, when you start digging into it. For our purposes, we're going to start with the definition of number. We're going to just say that numbers are quantities in this class. We're going to say numbers are quantities. And we'll give you some models that will help represent how do negatives fit into that. But for right now, we're going to talk quantities and understand, after we do all this math with the model of quantities in our head, if someone wants to come over and do calculus with clock time, excellent. They want to do calculus with computer science and the numbers over there, it still works. So, like, all of this is just going to be, we're going to start from something that's simple and tangible, and we're going to build up from there. So we're going to start with numbers are quantities, while understanding that that's not all numbers could be. It comes from some ancient origins. Now, you might think that numbers are a given. They're absolutely not a given. Humans are about 315,000 years old. That means you go 315,000 years in the past and you look at somebody, they're going to look pretty much like we look today. Numbers are only about 44,000 years old. That means that most of humanity has existed without numbers and has existed, therefore, without math. We've even got some cultures that continue to represent in their language that they don't have numbers, words for numbers above 5. The Amazonian Munduruku, like, culture does not have a word for over 5. After 5, you describe it as many, right? So there's a way of being able to have like a representation, because if it doesn't come up every day, like, do we really need it? That's the question. Even in Roman numerals, there is not a Roman numeral. There was not a number that the Greek culture respected that was above 10,000. Like, that was it. That was the biggest number anybody should ever need, ever. And we're talking, why would we have numbers at all? Well, mostly it's for kind of tallying. Some of the oldest origins, you can find a stick like this where you'll put notches in it. And that way, if you take if you have a shepherd who takes their sheep out to pasture and you let all the sheep go free, you want to make sure all the sheep come home. Otherwise, you got to go looking for one. So we've got a way of kind of tabulating and counting these physical objects. So that's going to be our first origins. We're going to talk about the natural numbers. So the natural numbers are our nature's numbers. They're your counting numbers. They're the numbers that you would go and teach a small child, right? That's what the natural numbers are. And you can think of them because they're the nature numbers. I have a 1-year-old puppy dog. If I go and I pull 3 cookies out of the cookie jar and I give the cookie dog 2, that dog's going to stare me down for the 3rd. Like, that dog knows there's another cookie, that it is like, it can count. So we're talking about the nature numbers, the numbers that people can represent with physical quantities. 0 is a tricky one. Believe it or not, 0 was not invented for quite a while, and it came out of India first, because you don't use 0 in language very much. If I ask you, how many spaceships do you own? Most people do not say, I own 0 spaceships. Most people say, I don't own any spaceships. They say, I don't have any spaceships. Like, 0 as a word does not come up. Why would you want to represent nothing? But we'll include it because it is something that does represent a quantity, and not having something could be a little bit represented. So we'll talk about the natural numbers as being the 0, 1, 2, 3 is the ones we could get a small child on board with. Do I still have this poll up? I want to see. All right, hopefully that made the poll go away now. So we got the natural numbers. Those are what we're going to begin with. And it begins to emerge within us this idea of axioms. Now, axioms are the way that mathematics starts. Mathematics, again, starts with something, then we apply logic on top of that, and then we conclude something. And if our beginning was true and we did nothing but logic in between, our ending must be just as true. That's the whole game we're playing in mathematics. So when we're talking about numbers, we have an assumption that we're going to start with. And it's this assumption that says, if I give you a number and it represents quantities, there can always be one more than that. This should be a pretty safe assumption, right? So if we're going to define some numbers, we have this ability to kind of continue growing in the numbers as far as we would like. Now, notice that that doesn't give us most of our numbers. That keeps us in the naturals. It barely even gives us to 0. There was not a Roman numeral for 0. Like, 0 was not a common number. And again, like I said, it came out of India, actually. India was one of the first places that was using a different numeric system and interacting with Western culture. Western culture was working with Roman numerals way up until like the 1500s, 1600s. And all of a sudden, here comes India and the Middle East, where they're talking about the Arabic numbers, these like the ones we have on our keyboard today. And they needed a way of being able to represent 3 versus 30 versus 300. So 0 was primarily just a placeholder. And then it eventually was something that we accepted as another number. So we've got our counting numbers. We'll add in 0 in there and call that the naturals. What about negatives? First examples of the negatives come about 2,000 years ago, mostly out of China, where China was using different colored rods to represent debt versus the money that was collected. So you'd be able to kind of cancel debt after there had been a payment, and you could use the different rods to keep track of this idea. In the 1700s, that was about the time that Western math came up with negatives and accepted them. We've got people who founded calculus. The guy's name is Leibniz, Wilhelm Gottfried Leibniz, invented calculus, like helped come up with calculus and compile it, who believed that negatives were not like good answers. Like they didn't hold a place as a number. So like we were talking like, well, it took a while for Western Europe to get on board with negatives. Meanwhile, negatives have been used by other cultures for quite a while. We'll represent it mostly using a model of piles and holes. So this is how I would like you all to kind of think for our very basic general baseline of like, what is a counting number? Let's imagine we have a sandbox. Now, if this sandbox is level and has no detail, we'll call that 0. Now, if I'd like to represent 1, then I could represent 1 pile in my sandbox. That will be 1. And if I'd like to represent 2, that's going to be 2 piles in my sandbox. And we kind of get the idea. That way, if I wanted to say what is 1 plus 2, that would just be a combination of the 1 and 2 piles in my sandbox. That would give me 3 total piles in my sandbox. And we get this idea of being able to do addition and counting. If we want to talk about what are negatives, the best way to read negatives off as a sentence is to just replace negative with opposite. So if we want to talk about the opposite of a pile, we might talk about a hole. So we might say that -1 is 1 hole in the sandbox. So now we get this idea of saying, what is 1 plus -1? Well, we could think of that 2 different ways. We could think of that as a sandbox with a pile and a hole, where I can use the pile to fill the hole. Or I could think of it as 1 minus 1, where I had a pile and I physically went in and removed it. Either of those gets us the same reference point of the sandbox at the end. So this is a way you can think of positive and negatives. Now, because we'll be doing a lot of geometry references in this class, another way we can look at it is we can look at it as if we are drawing it from above. We can imagine that we've got these little squares. We'll call these little 1 by 1 squares, where their dimensions are 1 by 1. So we've got a 1 object. And if we wanted, we could also make like a -1 object. We could either shade that in so it looks different, almost like we're looking at a hole from a bird's eye view. We've got a pile that's protruding out of the page and a hole going into the page. Or you can sometimes, to save the shading, just label it as a -1. And then you've got a whole bunch of models this opens for us. We can think of it as like a matter and antimatter, where if these two combine, they annihilate each other. We can think of it as a pile and a hole, where one is allowed to kind of complete the other back to 0. All of these are fine. We're just trying to give a visual. And now that we have this visual, this helps us combat some of those questions we had from the other class. Like, is 0 the same thing as 1? No, it can't be. It can't be, because I can look at it through this model and see they are different. So we have something that we can physically reference if we are ever confused and overwhelmed by these ideas of forever. All right, let's talk about the integers a little bit. Integers are going to just simply come, like, they're going to be your positive and negative versions of the natural numbers. Integer comes from the same root word as integrity and integral, meaning complete. So these are your complete numbers. These are the numbers with no trailing extras, no and 0.2, no and a half, nothing like that. We're just talking, it's nice, complete integers, right? It comes from like integrity, to be complete, to be whole within your, like, that's what we're talking about here. And subtraction doesn't exist unless we accept negatives. So we have to allow for negatives. Otherwise, I can just decrease to 0 and I stop. Once we allow for the idea of there being negatives, then we can do subtraction as far as we want. So integers is the model of numbers we must accept if we would like to be able to do even just addition and subtraction. What about the rationals? I remember seeing this a lot when I was a kid. I saw rational and that confused me, because I thought rational means like makes sense. I thought rational means that it makes sense. That's not what this is talking about at all. Rational, for the rational numbers, means it comes from a ratio. It means it comes from a ratio, meaning it's a fraction. So the rationals are your ratio null fractions. They're your fraction numbers. You might think that geometry, like we said last class, was invented by the Greeks. It was absolutely not. It is primarily an African and Middle Eastern mathematical form. And that's why we have giant geometric structures that are in Egypt. So we have geometry and the need for being able to construct things, meaning to cut things into pieces and fit them together. So about 3,800 years ago, you've got Pharaoh who's trying to build all these large structures and needs to be able to implement a tax system. And the best way to implement a tax system is to charge the people who have a lot of land the most money, because that's a good visual for who has money when people can go and hide their wealth. So that's why we need to talk about this division. How much more land does somebody have? What is it like to split something amongst people? So that's what we're talking about when we talk about the rationals. The rationals are anything I can represent as a fraction, where I'm putting complete integers, those whole numbers, on the top and bottom, the positive or negatives. All right, that's about all the definitions that we're going to do now before we start really getting into some base ideas. But you can see that numbers are not something that was a given. It's an invention. It's an invention by humans to try to model a logic, the logic of decrease, the logic of debt, the logic of splitting evenly. So with the acceptance of the rationals, we get our second axiom. If we have a natural number, then the negative of that must exist, right? And 1 divided by that fraction must exist. Because if I have 1 divided by that fraction must exist and the negative of that, then I can do addition and subtraction up from there to get all the rest. So this is, again, this is an acceptance. We are agreeing that division and subtraction make sense. We're choosing that, and then all the rest we're going to do on top of it. So what are some consequences? Well, it takes a little bit until mathematics begins to become more than just a problem-solving tool. One of the best examples of this is we've got Pythagoras. Pythagoras, about 500 BC. We all know him for his triangle theorem. Truth is, he should be known for a whole lot more and less than that. He's a cult leader. That's the best way to describe him. He had a cult where he led people towards mathematical religiousness. Like he had people who vowed themselves to him. There were legends crafted about this guy. He walked around wearing white, having a wreath. He had legends about him having a thigh made of gold that he showed off at the Olympics. Like the guy was just like, we're talking like this guy was out there, right? Believed in the magic of numbers. That one I can understand a little bit because there began a culture in Greece where they began to recognize the idea of splitting something in half or in thirds was not only something I could construct and represent easily, but also corresponded to music. Right? If you have a guitar string and you hold your finger down on the halfway mark and you pluck it, you will get a pleasing sound. If you go to the third way, you'll get a pleasing sound. But if you put your finger down randomly and struck it, you will get an unpleasing sound. So there became something about the resonance and the workings of nature that began to reveal themselves through mathematics. It became a way of understanding the world. But he didn't come up with the theorem. There's plenty of evidence that says the Pythagorean theorem was actually discovered way earlier in Iraq. He is just one of the people who helped make it quite popular. So we get the Pythagorean theorem. And we're going to talk about that one because Pythagorean theorem is great. Let's talk a little bit about this. Again, in my class, there are no rules. So I'm not going to give you a formula for us to be using if we cannot understand it at least a little bit ourselves. So we all know the Pythagorean theorem, a squared plus b squared equals c squared. That's excellent. But why? That's the immediate question we should all want to ask. Because if I don't know why it works, there's really no, like a computer could do that instead of me. Like, why does this work? It's a beautiful, beautiful story that's totally worth understanding. So let's go into it. It's a super, super easy proof. So you'll want to sketch this down alongside me. Imagine we have a right triangle. And because I'm going to be wanting to explore the lengths of this triangle, let's give them some labels. Let's call this side A, we'll call this side B, and the other side will be C. Now, if I am playing around with this, I might imagine that this is something like a tile, like a physical tile that I can use to make patterns and art with. So let's make a little bit of art. Let's take this and begin to place it in a little modern art structure. So I'm going to take the exact same triangle and I'm going to repeat it around. So it makes a little bit of like an artistic picture frame, if you will. Right. Exact same triangle, repeated around. So it forms sort of this large square. And I can label some of these sides just to keep track of it. We've got the long side B, the short side's A. So that means this is B and this is A, and this is B and this is A, and this is B and this is A. And on the inside, we've got C. Now to keep track of the fact that this was a physical thing, I'm going to go ahead and give it a little highlighting. I'm going to highlight it a little pink here. And I'm going to highlight these pink as well. And so what we're going to see is we've got some empty space in the middle. We've got some empty space. We've got the triangles, the physical triangles all around the outside, and then some empty space inside that. How much empty space is that? Well, the empty space would have to be a C by C space. In fact, it's a C by C square. So that might be a C square. That would be the size of how big the empty space is in the center. Okay, that's fine. Well, I can take those tiles and I can move them a little bit. So I'm going to sketch out the frame of that large square that we have and just watch as I move the tiles around. So I'm going to start off with still got this tile up here in the top left. I'm going to take the other tile and I'm going to scooch it on up here. So I'm going to take it, I'm going to scooch it on up so that it comes and touches with the next one. So if I scooch it on up, it's going to nest nicely right against it. And then on the other one, I already had a triangle that was sitting right here. And I'm going to take the one that was down here. I'm going to move it on up so it kind of nests right up against it. So I'm going to move it on up so it comes right here. And now I've kind of got everything moved within that frame. Give it a little highlighting so we keep track that these are just the physical tiles. I'm taking them and I'm sliding them around. Now what we can see happened is that that empty space in the middle has to still be there, but it's just simply not in the middle anymore. It's somewhere else. I can kind of section off those two regions into two different regions, because take a look here. This is the long side, so that would have to be B, and this is the short side that's A, which means that this has to be the remaining difference. That has to be B right there. So the inside that I have here, this is a B by B space. This is a B square. And over here, I've got an A because it's the short side and B is the long side, which means that A has to be what's left over. So this little space inside here is a by A space. That would make that an A square. So if you take the physical right triangles and you do this with any size, because I didn't give it numbers, what we found is that the empty space represented by A squared and B squared has to always be the same as what was originally represented by C squared. And that's our Pythagorean theorem. Now tell me that's not better than just being handed a formula. Like, oh my golly, like that's just like that's cool. That's like a party. Like you could sketch that on a napkin while you're bored. Like that's just good, right? Like it has to be true. It's not a it works. It's a insight into nature. Like you can't break that if you try. It has to work. So there you go. That's the Pythagorean theorem. Has to work. As we're going to see, it's going to cause a whole bunch of chaos in Greece, a whole lot more than people were expecting. Because you've got to remember that this is these kind of truths, these principles, the constructions, the philosophy. This was the way of life. This was an exposure. This was a point of pride for many Grecians. And when we get into proofs like this, and we start to challenge that, oh my golly, things start to get upset. So we got this guy right here, Hypatius. Hypatius is one of the students of Pythagoras, really devout, doing his thing, right? Pythagoras hands him an equation and says, hey, a squared plus b squared equals c squared, and he's going, got it. He's like, great, we'll do it. Like running through with it. The problem is that it's gonna cause him to get murdered. So we've got Hypatius here who's gonna get murdered because he's doing math too good. To show you what ended up happening with Hypatius, we're gonna have to start stepping into the realm of formal proofs. And so understand that proofs start with definitions and axioms, and then they're gonna do nothing but logic. And we're going to look at consequences that happen as a result of that. And if whatever consequence we get to has to be as true or false as what I started with, if I did good logic. That's the entire theory we're playing with here. So the strategy we're about to show right here is we're about to show that this square root of 2 number is irrational. Now, notice that if we are successful, that means that this entire religious obsession that ancient Greece has with numbers, we're about to throw this like up in the air, because they are thinking the entire world is governed by fractions. There's no such thing to them as the number line. There are whole numbers and there are splitting of whole numbers. Like there's nothing else. So how we're going to show that this has to happen is we're going to pretend that the square root of 2 is not irrational. We're going to pretend it's rational. It's something that can be represented as a fraction. And then all we're going to do is explore that consequence. And what we're going to find out is that in that exploration, we're going to realize that this fraction is stupid. Like it doesn't make sense. It doesn't work. It is literally going to create a paradox. We're going to find out that this fraction can both be simplified, like fully simplified, and not fully simplified at the same time. That can't happen. You can't have 1/2. 1/2 is simplified. You can't make it more simple than 1/2, right? If you have a number that can be made more simple, then it is made more simple. If you have a number that is simple, there's no more on top of the simple. It's just is. So we're going to see that for square root of 2, that's what breaks. All right, so we're going to begin. Let's imagine that we have the square root of 2. The square root of 2, we're going to pretend can be written as a fraction. We're going to imagine that it's a simple fraction. So I'm not talking about like other ways of representing it in big, complex gotcha moments. I'm just saying, can it even happen? If it can happen, then we should be able to do some natural things. We should be able to take this and multiply both sides by q, and then we would get square root of 2 times q would be equal to the numerator. That should work. In fact, on top of that, I should be able to square both sides, and I would get 2q squared equals, that's a little typo, that should be p squared. Okay? This is a natural thing. We're just moving some symbols around, right? It has to happen if the beginning thing is true. So we're just simply saying that if it's a fraction, then I could also write the fraction like this. Okay. So I'm going to go ahead and summarize up in these slides because some of these take up multiple slides. I'm just going to show us where we're at in the story. We already started like, if this is a fraction, then I can represent the fraction this way. Well, a consequence of that is that means that I've got over here 2 times a number. 2 times whatever q squared is going to be a number, and 2 times that creates 2 times a number. Well, 2 times something makes it even. So that means that p squared, whatever this number is, has to be even because it's 2 times something. So p squared is going to be even. Excellent. So we're going to go ahead and write that down. P squared has to be even. On top of that, if I take this and I break it down a little bit, I'm going to bring it down here. We're going to have 2q squared equals p squared. I recognize that p squared is even. Also notice the only way to make an even by multiplying something times itself is that that must have been an even times an even. Like if you do 3 squared, 3 times 3 does not get an even number. 5 times 5 does not get an even number. It's got to be, I've got a 2 that's appearing somewhere as a factor here and somewhere as a factor here. So that means that each individual p has to be even, and it means that I can break this as saying I have even times even, so that even if I look at the 2q squared and I say that maybe this 2 came from this even, it still makes q squared have to be even as well. So the important thing to recognize is that through just exploring this kind of flattened structure, we're going to recognize that both p squared has to be even and q squared has to be even. And that's just from playing around with where 2 appears as a natural consequence. All right, I'm going to pause here for just a moment. Any questions I can help with on why we're where we're at in the proof? So you can raise your hand, you can throw something in the chat. Again, I've got this proof written out in the notes, but I don't have the summary and the strategy. So this is just you all kind of trying to jot down like what's going to help you recall the general structure, and then you can go put those into the guided notes so that you can follow along and kind of re-iron out the details. All right, I'm not seeing anything here. Okay, well, notice where we're at so far now in the story. We have said that if I can represent this as a fraction, then that means I'm able to get a number on the numerator and the denominator that are both even. Well, that doesn't work if I started and said it was simple. Y'all see that? Like if I started with this is a simplified fraction, and then I explored it and I naturally found out that it's also not a simplified fraction, I've created a little bit of a paradox here. That means that square root of 2 is a fraction that is both simplified and not simplified. That doesn't work. That can't happen. You can't be both true and false, both on and off. You cannot be a fraction that can't be simplified anymore and is also the simplest it could possibly be. It doesn't work. So what that means is that in either of these ways that we connect the dots, we either have to choose that if we allow square root of 2 to be a fraction, then it must be a fraction that makes no sense, or maybe we just started wrong and this thing isn't a fraction at all. And that's where we get the conclusion. The conclusion is that this is not a number that can be represented as a fraction, because if it is a fraction, that fraction that it is makes no sense. Like it doesn't work as a fraction, so it must not be. Now that's eye-opening, to say the least, because now the entire world of the rationals just got blown wide open. People thought that you had numbers from things you could count, numbers from things you could split, and all of a sudden we found out there are numbers that exist that we can't even describe, except for as a story. Like, think about the square root of 2. The square root of 2 is not a number, it's a story. It's saying if I could square root 2, then I would land somewhere near 1.7-ish. But 1.7-ish is not square root of 2. Square root of 2 is square root of 2. Like, square root of 2 is literally us trying to describe a number I can't touch. I can only get close to. I can only work my way towards. Like, it's only a thing that's there, but I can't touch it. People did not like that. All right, so conclusion. There must not be a fraction that represents square root of 2 because that didn't make any sense if it did. So it's not rational. We'll call it something else. We'll call it the irrational. So consequences, the moment that Hypatius found this and reported to Pythagoras and all of his people, he was promptly thrown off a ship and drowned. So he was murdered. But nonetheless, like, you can't, the ancient civilization couldn't close Pandora's box once it was opened. And all of a sudden, irrational numbers are popping up everywhere. Cube root of 2. Cube root of 2 is also an irrational number that came up as a part of ancient legend, because in a time of drought, people went to the oracle. You all know that there were like oracles that helped to like provide wisdom and religious guidance. They went to the oracle and said, how do we end the drought? And they said, take the cube altar to Seer, like, make that twice as large. Well, to make that twice as large, they had to double a volume. And to double a volume, you have to increase each side by the cube root of 2. And the cube root of 2 is irrational, and no one knew how to figure that out. So like, it became a thing that started to plague society. Irrationals were not widely accepted. But together, we know that they are just as good at representing logic and models and construction today as they ever were. So we've got the number line. The number line is our primary method of being able to represent all of the naturals, all of the integers, all the rationals, and all of the irrationals together. This is a collection that you can think of as the positive and negative lengths. So if you can imagine it as a length, then it is something that belongs on the real number line, and its negative a counterpart. Now, we might think, if I asked you all, this is again another insight into how difficult the word forever is. If I asked you how many rationals are on the number line, you would probably say there's an infinite number of rationals. On top of that, you'd probably say there's an infinite number of counting numbers. And you'd probably say there's an infinite number of irrationals on there. And all of that would be pretty kind of correct. But we're going to find out that they're actually different in the quantity, so much so that if you randomly put your pencil on a number line, you are 100% guaranteed that your pencil will fall on an irrational number. That the likelihood of you choosing a rational or counting number from the number line at random is not almost 0, but literally 0% likely. We're going to kind of dig into that here. All right, so follow me if you will. If you have any questions, feel free to let me know. We're going to take two different facts here, and we're going to combine them in a creative way. Here's the first fact. I can represent the fraction 1/9 as 0.1 repeating. And you can use a calculator if you'd like to verify that. If you don't trust the calculator, you can do it with long division. It's totally going to work. Also, I don't have to represent it as a decimal. I could represent it as a series of fractions added together, because we call this the tenths place. This is 1/10. So I can represent that as 1/10. And this is the thousandths place. So I can represent it as 1,000th. I can put that over here as the hundredths place. I can put that as the hundredths. And then I've got the thousandths place. So this is the equivalent way of being able to describe 1/9. Either of these work. They create the same thing. So that's fact 1. Fact 2 is that if I am creative, I can create a matrix, a list of every fraction number that is in existence. Okay, so here's how I've organized it. I've started off, we got 1/1. If you go down the matrix, you can see that that's now 2/1 and then 3/1. So we're going to change the numerator by 1 every time we go down a row. And we're going to change the denominator by 1 every time we go over a row. Now, we're only doing the positives here just for simplicity, but we could absolutely do the same thing with the negatives, and we're not going to change the result at all. So right now, I just want us to recognize that this has every single positive number that could work as a fraction, as a number of the rationals. Let me make sure where I'm drawing from. There we go. So what we're going to do is we're going to zigzag through this matrix, and we're going to make a list. So we're going to take this, and we're going to zigzag through it. And from that zigzag, I can make a list where I start with 1/1, and then I go to 1/2, and then I go to 2/1, and then I go to the next row would be 3/1, and then from there I go to 2/2. So if I repeat a fraction, that's fine, but I'm just simply saying I can list them all, and I will get to them all. So those are the two facts. One, I can make a list that has every single fraction number in it, and two, I can represent 1/9 as a bunch of addition. All right, those are the two facts. Let's take a look at how we can creatively use those. Imagine now that instead of just having 1/9, I'm going to make this 1/9 of an inch of ribbon. So 1/9 of an inch of ribbon. Here's some ribbon. And I cut it off of my little spool. I've got 1/9 of an inch of ribbon, and I'm going to take that 1/9 of an inch of ribbon and I'm going to cut it up more. And I'm going to use the little pieces of that 1/9 to cover places on the number line. So I'm going to cover the number 1 with the first cut, this 1/10. I'm going to cover it with a 1/10. And then I'm going to go on to the next number in my list, and I'm going to cover it with a 100th. So I'm covering up every single number on the number line with ribbon. Now, once I've covered up the number 1, we'll agree that there's some excess. So I've definitely covered up 1, and I've even covered up some numbers off to the side. That's fine. I'm just simply saying we can cover up every single rational number with some ribbon, and that it's not going to be a total amount of ribbon more than 1/9 of an inch. All right, so 1/9 of an inch of ribbon is all I need to cover every fraction on the number line if I'm creative about it. Thus, the rationals must be together no bigger than 1/9 of an inch. You want to talk about the negatives? Fine. Repeat the exercise over there. You get 2/9 of an inch. Like we're just covering, like I can cover it all up with ribbon. And I can cover it all up with a specific amount, 1/9 of an inch of ribbon. Well, there's nothing special about the 1/9 of an inch of ribbon. We could repeat this again with a 90th of an inch of ribbon. I could start with a 90th of an inch of ribbon, and then recognize that that fraction is that I don't have the tenths anymore. I just start with the hundredths, and then that's plus the thousandths. So in other words, I can go through this whole thing again, and I can cover up the number line. I can cover up every fraction with less ribbon, but I still cover everything up. Well, I can repeat this again, and I can cover it up with less ribbon. I can cover it up with a 900th of an inch of ribbon. So now I must be able to cover up all the fractions with less than that even. Well, I can repeat this game again and again and again. So that means the total size of the rationals must be some size that I can cover up with a 1/9 of an inch, a 90th of an inch, a 900th of an inch, and however small I want to go. Well, then that means it must be a size that can always be covered up by smaller. There's only one size that works for that, and that would be 0. So that means all of the fractions, the size of all the fraction numbers, if you took all the rationals, you pulled them out and you grouped them together and you measured it, they have no size. There's zero in measure, 0 in total amount of the number line. Now that's weird, because the consequence of that is if you have the number line and we split it into the rationals and we split it into the irrationals, then that means that all of the rationals take up no space. That means that the irrationals take up all the space. That means most of the number line, not most of the number line, all of the number line size is due to irrational numbers. There are so many more irrational numbers than rational numbers. So all the rationals add up to just 0 in length. The irrationals, on the other hand, add up to all of the length. And this again shows us a weird paradox that infinity is present in. That means that if we think of all of the rationals, all the fraction numbers as just being 0 width numbers, 0 width points, they're just points and points and points, and we add them together, that's a bunch of 0 plus 0 plus 0 plus 0 equals 0 for the rationals. But for the irrationals, even though every number still has no width, we do 0 plus 0 plus 0 plus 0 a whole bunch of times and we get infinity. So we had a whole bunch of zeros added up to a 0, and then a whole bunch of zeros added up to infinity. Like that's about as opposite as you could possibly get. What's happening here? Well, the consequence that I want you to take away from all this is think about this. everything you thought is a normal counting rational size in your life, most of them aren't. Your height, like I'm 6'2", I'm not 6'2". I'm an irrational number that's pretty darn close to 6'2". There's like, I am not a rational height. Your desk is not a rational area. Volumes, none of the volumes you've ever encountered in your life ever have been solid, normal, nice. No, they're all irrational because they exist on a continuum of measurement. And if you choose a number from that randomly, you are guaranteed for it not to be rational. So anybody who's like, oh my golly, like the calculator didn't give me a nice answer. Yeah, expect that out in the real world. That's how the real world works. If you want to have like nice numbers, you better be talking about something that's not on a continuum. Like sure, one pencil and another pencil makes two pencils. Got it. You're not going to have 2.1 pencils. But if it can exist on a continuum, if there's the ability for in between, the entire world actually exists as an irrational measure. All right, so let's talk about infinity for a little bit. This is the way that I like to draw infinity, to give you a model for like really what are we talking about with infinity. I'll sketch it out in real time. That's from the last class. So let's talk about infinity a little bit. Infinity is a number. You are welcome to say it is a number. The reason why it's not often told to people that it's a number is because it's not a real number. And that's not to mean it's not realistic. It's to mean it doesn't belong on the real number line. The real number line, remember, are lengths. There's no such length as forever length, right? We could not possibly try to cut that down and imagine it. So the infinity is a number, but it's a number that represents forever. So the way you can draw it, if you'd like a reference for it, is you can sketch your normal number line. And you got your 0 and your 1 and your -1, etc. You can think of it like that. And then we all know the number line goes on forever. So you can kind of put on a little bit of like foreverness here. And you can think of infinity not so much as a number, but more as a boundary. Think of it as a boundary. So you can sketch an infinity here as a boundary. And beyond that boundary, you have the infinite. And below that, you have the finite. So our finite numbers are going to be our real numbers, the ones that we can actually have as a good answer for the end of an equation. But our infinite numbers, this is the realm that's giving us so much grief. This is where we just found that there's an infinite size that describes the irrationals that is bigger than the size that describes the rationals, even though both of them are in the realm of forever. So there's a different ranking that's up there. It's not on a line. It's not something that can be compared to the line easily. If we want, we can think of a negative infinity down here. That's totally fine as well. And again, beyond that, you've just got the negative infinite. Okay. So that's why we can't do infinity plus 1. It doesn't exist on the number line. Plus 1 on the number line means move up 1 on the number line. Times 2 on the number line means take the number line and stretch it like a rubber band until it's twice its length. That's what times 2 means. It takes 2, moves it to 4. It takes 4, moves it to 8. Like that's what happens when we do multiplication. So if we're talking about the infinite, it doesn't behave by those rules. It's off that number line. Now, calculus, as we said, is going to try to attempt to describe this. As you can see through the solutions we had to do for square root of 2 and the solutions we had to do for what are the size of the rationals and the irrationals, we can't approach these questions head on. We've got to be creative about it, because the moment you allow forever to be an answer, we lose clarity on what type of forever are we talking about. The big kind, the somewhat big kind, the really, really big kind. Like we don't have a thing to quantify it. So we don't do any of these calculations directly. How do we draw infinity? I already showed you that one, so that works out great. So let's go ahead and give a little bit of insight as to what we're going to do for next class. We're going to talk about how we can draw negative numbers some more, right? We talked about that a little bit today, but we're going to start to bring those models in. Why is a negative times a negative equal to a positive? Again, this is a rule. Many of us know this rule. If we had to explain it to a 5-year-old, could we? because we're going to need, like, we should know why that works. I've heard you can't divide by 0. This is a rule. Again, I hate rules. Rules don't belong in my class. Unless you can convince me I can't divide by 0, I'm not going to believe you. Like, did somebody just decide on this? Is it a law? We're going to figure out what's actually going on behind the scenes here. And then lastly, why do we call it x squared? Because I just see an x with a little 2. I don't see a square. If you all see a square, you can let me know. Like, we're going to have to figure out, like, why is this called square? We'll get into that. So before next class, what I would recommend you all do as a reminder is you should go onto Blackboard and you should pull up the guided notes. So I make those available within 10 minutes usually of getting out of class, and I post the recording within a couple of hours after that. So just to kind of show you, if we take a look at the guided notes, there's some density to them this time. And I've done that to try to save you so much writing. We've gone through the numbers, the natural numbers, all of the axioms we have, but I've left some space, like, how would you draw the thing we drew in class? I've left some space. How did we describe and define the Pythagorean theorem? I've left some space for how did we approach the proof for the square root of 2 is not rational. Now I've got the proof below here so you can reference it, and that'll help get you some practice with how do I read through all this dense logic. You just need to summarize it for yourself on top. It's to help guide you. It's to give you a chance to speak to future you. And as I said, I do pull a lot of inspiration for the quiz questions from here, so I would strongly recommend you go on, print it off, and see how much you recall. Otherwise, I'm going to stick around for a little bit if anyone has any questions, and I'm going to make this go live. If you want to stick around for a little bit, happy to talk with you. Otherwise, I'll see you tomorrow. Hey, Felipe, how you doing? Felipe, you good? Otherwise, I'm going to be stepping away. All right, going once, going twice.